You're right. Here is a much longer, broadly developed version in one continuous text, smooth and ready to be read by a voice talent, without bullet points or headings. Science is fascinating, immersive, and gives us tools that let us see far beyond the horizon of everyday life. But science is also demanding. It requires honesty about facts, patience with complexity, and humility in the face of uncertainty. Admiring the beauty of an idea is not enough. What's needed is the painstaking work of checking whether that beauty withstands the test of reality. Even at a basic level, science forces us to think clearly, precisely, and logically. It requires us to set aside our wishes and convictions and look at the world as it is, not as we would like it to be. The further we go into advanced fields, the more we see that genuine understanding demands years of practice, painstaking analysis, teamwork, peer review, and critique. Science is a conversation among thousands of minds, and its strength lies not in infallibility, but in its capacity for self-correction. This is precisely why, alongside genuine science, a thicket of ideas flourishes that only resemble science on the surface. Pseudoscience eagerly dresses itself in technical vocabulary, uses diagrams and terminology, yet skips what matters most in science. Testable predictions, exposure to criticism, publishing results in a way that lets others verify them, and, above all, a willingness to abandon a mistaken claim when the data say no. One such idea is the electric universe concept. Its proponents talk about a cosmos woven from currents, about galaxies and stars allegedly powered by electricity flowing along invisible plasma cables, with gravity pushed to the margins or even rejected. It sounds fresh, spectacular, and enticing. After all, energy and light suggest dynamism, the intuition of electricity, lightning that splits the night sky. But once we start asking questions, once we confront this story with hard data, the spell breaks. Let's look at the sun. In stellar physics, it's the best studied object of its kind, our standard, our reference point. The standard picture says, the sun shines thanks to nuclear fusion in its core, where under immense pressure and temperature, protons fuse to form helium. The result is photons carrying energy, the warmth we feel on our skin, and neutrinos, almost ungraspable particles that pass through matter like ghosts. If fusion occurs, neutrinos must exist. If the sun were merely a plasma lamp powered externally by cosmic currents, neutrinos should not be there. And yet, we detect these neutrinos. We observe their flux, consistent with the predictions of helioseismology and thermonuclear reactions, and in more recent experiments, we can even reconstruct the sun's shape in neutrino light. This is not a detail. It's a direct consequence of the process that powers the star. Any theory that denies this flux does not match reality. A second line of evidence comes from the sun's spectrum. If a star is a hot ball of gas, its radiation should be nearly continuous, with a characteristic intensity distribution dependent on temperature, plus narrow absorption lines from the cooler layers of its atmosphere. And that is exactly the spectrum we observe. A plasma lamp, by contrast, produces discrete line spectra typical of electrical discharges. You can verify this in the lab. Researchers saw it already in the 19th century. There is no room here for wishful thinking. The lines are where they should be, and the continuum is exactly what thermal radiation from a body at the photosphere's temperature predicts. The electric picture of the sun does not survive this test. But the electric universe goes further. It claims that galaxies and cosmic structures are products of currents, that gravity is mistaken, and general relativity an unnecessary layer of mathematics. Enter two of modern cosmology's most puzzling hypotheses: dark matter and dark energy. Critics like to say scientists made them up ad hoc because the rotation of galactic arms is too fast. And indeed, spiral galaxy rotation was a shock. When astronomers measured the speeds of stars and gas in the outer regions of galaxies, they found rotation curves don't fall off as they should if only visible matter mattered. The arms rotate faster than the luminous mass alone would imply. This wasn't one galaxy, it was a pattern repeated in dozens, then hundreds of cases. So a hypothesis emerged. There is additional mass, invisible in light, that interacts gravitationally. We called it dark matter. That hypothesis immediately began to spawn predictions. If dark matter exists, it should affect the bending of background light, gravitational lensing, and show up in the layout of cosmic structures, in the anisotropies of the microwave background, in collisions of galaxy clusters. Then came observations and simulations that repeatedly confirmed that this invisible scaffold helps us understand the map of the universe. It wasn't one bandage for one wound, it was a thread running through the entire labyrinth of cosmology, from the early universe to today's clusters. Dark energy is a different story, equally troublesome and even more counterintuitive. Comparing the brightness of distant supernovae showed that the universe is not just expanding, it's expanding ever faster. In a simple picture, gravity should slow expansion. And yet, we see acceleration. The simplest correction to the gravity equations is the cosmological constant, a vacuum component that pushes space to expand. We called it dark energy. And just as with dark matter, scientists began checking whether this addition explains other data, how large-scale structure evolves, how baryon acoustic oscillations are imprinted on the distribution of galaxies, how all these measures line up with each other. It's not that scientists paper over ignorance with inventions. Rather, they have the courage to admit that our equations, intuitions, and data point to components we do not see directly, but whose presence best holds everything together. Perhaps in a decade or 2 or 3, we will name them differently, identify particles, grasp the microphysics of the vacuum. But today, based on what we know, dark matter and dark energy function like good tools. They predict and allow us to move from questions to experiments. The electric universe has little to offer here. Instead of predicting, it retrofits. Instead of calculating rotation curves from mass distributions and potentials, it points to look-alike images of discharges and nebulae and says, this looks similar. But nature is tricky. Visual similarity is not a physical argument. The argument is an equation that survives the test of data. In plasma, which truly is ubiquitous, marvelous things happen. Filaments, currents, oscillations, instabilities. The problem is that on cosmic scales, plasma is generally quasi-neutral, and long-range electric fields are screened. Gravity, on the contrary, always adds up positively. There is no gravitational plus and minus that cancel. That is why gravity rules the largest scales of the cosmos. Electricity is magnificent locally, in solar flares, in jets from accretion disks, in polar auroras, but it does not replace gravity as the architect of large-scale structure. When we talk about black holes, relativity, and space curved by mass, the electric universe prefers to look away. Meanwhile, the data speak loudly. We have recorded gravitational waves from merging black holes and neutron stars. Their time profiles match general relativity's calculations with stunning precision. We have imaged the shadow of a supermassive black hole in the center of an elliptical galaxy and in our own Milky Way. Images that require careful accounting of space-time curvature just above the event horizon. Around black holes, we see particle jets stretching thousands of light years and regulating the growth of their host galaxies. The relativistic description is no longer mere mathematics. It is the language of technology and observation. Without relativistic corrections, GPS would drift by amounts we can feel in daily life. Look at how planets are born. If stars electrically give birth to planets and smaller stars, we should watch solitary stars later surrounded by random companions. In reality, we most often see protoplanetary disks of dust and gas, with rings and gaps where circulating grains aggregate and young planets sculpt paths. We see shadows cast on disks by tilted rings and spiral waves created by gravitational perturbations. It's a coherent picture, from molecular clouds through gravitational collapse to protostars and disks, and then to planetary systems. Electricity has its place in this account, in angular momentum transport, in magneto-rotational instabilities, but it is not a cure-all that magically explains everything. Proponents of the electric universe like to invoke Tesla, Alfvén, Birkeland, names that sound like seals of quality. Tesla was a technological visionary, but he did not leave a cosmological theory that passed scientific scrutiny. Alfvén is the father of plasma physics. No one denies that. But his broad cosmological speculations have not gained observational support. Birkeland described currents in the